part 4, I'm just going to run everyone through some advice on using BIOMEC algorithms and just BIOMEC in general for optimization of the MECSim. I'll probably put anything else I've forgotten in the other videos. It shouldn't be much. This will be quite a quick one, but I'll just give you some advice on using CMA-ES and Bayesian Inference, what loss functions to use and when, and what to look out for, right or wrong, in just analysis, and tips on what to do when things don't work. So first thing we're doing is advising using CMA-ES and Bayesian Inference. First thing is do it a couple of times. So if you have a data set of say, let's say 0.5 ferrocene millimolar ferrocene in acetonitrile, say. Right. This is a very fast system. Even if depending on the electrode you're working on, it's generally quite a fast system. An extremely fast system. But even if you were to say slow it down or stuff, you'll get multiple fits. Now, the first thing you would do is you'd identify what parameters to change. So first you'll set, say, parameters. For a ferrocene, you've got E, your E naught, your K naught, your RU, your diffusion, alpha, and your CDL. This is generally the most amount of parameters you can optimize for a E system. You could also change concentration as well, which you might want to do because it's in the acetonitrile will evaporate away, but that'll couple very aggressively to your diffusion. So first, just run like say 3 CMAs, CMA-ES. This will be quite a quick process. So you could run them at high accuracy, but you could just run 3 at like a moderate one, say something like 0.25, 0.025, I think, or the half recommended one anyway. So that would optimize down, 0.025 tol x. And what that'll tell you is that'll tell you if there is a stable, constant optimization. Now, you might want to try this with TCDS as well as a harmonic percentage method without Bayesian inference first, because you just don't know what's going on. So if you just got a DC method, just use TCDS. If you've got some Fourier transformed AC voltammetry data, do harmonic percentage as well. Ideally, these won't change much, but they might. So it's just good to confirm what kind of works and what doesn't. For all these parameters, you're going to have quite a few issues. What I've generally found, especially with my very brief usage of TCDS, it's a bit more difficult to get. And for all these parameters, it's going to just go a bit weird considering your resistance and diffusion. For harmonic percentage, because you just have more harmonics and they're more sensitive to these things, it can decouple resistance and diffusion quite well and get the data out. So that's a good way of figuring out whether or not you've got a good understanding first. So you'll have your harmonic data and your TCDS. So say there's a lot of difference though in your capacitance, double layer capacitance for your experimental data, and you're interested in that. So you're doing a study, say, of the effects of double layer capacitance in ferrocene for different concentrations of electrolytes. I strongly advise to use TCDS in this case, mainly because your double layer capacitance is going to show up in your DC component, your AC component, and your second harmonic. If you're doing anything with capacitance, I strongly advise TCDS, just because it only requires a single experiment. It gives a good fit, and I can just quickly show you some experimental data I have. So I've got some data here from the paper we published, and this is using a harmonic percentage method and TCDS. So the top one is TCDS. The bottom one is Hamper. As you can see, the posterior distribution calculated from harmonic percentage is nowhere near the true variation between it. Mainly because what's happening is basically the TCDS is just fitting every single bit of experimental data, whereas the harmonic percentage just grabs the mean or the most value of it and just fits that. So here you can see it's just optimizing for one because that's closer to what we're getting. And then all the other ones are just all over the shop. So if you're doing a study on capacitance, I strongly advise TCDS because capacitance varies a lot more between experiments. A similar thing occurs for E naught, generally just due to shift in the electrode potential. This can be, it's not too bad. It generally gives a good approximate value of the mean E naught. In saying this as well, harmonic percentage will not work if you're using a pseudo reference, because it assumes that all your replicate data are similar. If you're using a pseudo reference, there's going to be quite a bit of sway in your potentials, and it's going to make using the harmonic percentage method a lot more. So the two situations you want to use TCDS and harmonic percentage are TCDS for CDL studies and pseudo reference. Whereas the harmonic percentage is a lot better at using when you're fitting for a lot of parameters or when you need to get an initial idea of what all these values are. Yeah, I find the TCES is very likely to just couple strongly between two parameters, where FTA-CV only really happens for free. Other things that occur, so you probably, for CMA-ES, you're not going to see that, but when you apply that for Bayesian inference, you're going to see that happening quite a lot. Is just for coupling of parameters causing really weird distributions. Because when you find a point solution, it's quite easy, but when you find Bayesian inference, it isn't. So the initial free CMA-ESs are just to identify the best fit of the data and make sure there isn't multiple local minimas around that will just really, you'll struggle trying to identify. And yeah, when you're doing that study, you just use CMA-ES to identify what parameter values are you expecting for your mean, and also what loss functions are better. We also have loss functions based on Fourier transform and frequency domain. I recommend not using those because they don't give very good data, as seen in another image I'll just get up now. Yeah, they won't give very good things. So here's a plot in our published paper of the effects of different loss functions have on fitting all these parameters, and as you can see, just using the non-Bayesian versions of harmonic percentage and TCDS work really well. That's why I'm saying initially do one of these or two of these just to confirm what kind of values you want, and then extend that up to some Bayesian ones, which are going to perform a lot worse, but it should give you a good idea of what the response is. Cool. And that's CMA-ES. CMA-ES will also give you an idea of how long the Bayesian inference will take to do. As for Bayesian take to do, when it comes to applying the Bayesian inference, you want one normal distributions that all look like that. Now you can identify this using prob and feeder. You can identify this by just visually looking at it, or just for our hat statistic. One thing that will happen commonly is, say you set for prior distribution to some reasonable value, say 30, let's say resistance, and 150. What'll happen is your posterior distribution will just be like, nah, it's a lot higher, and it'll do this. If you're, and what this means is that you're sampling the posterior and it's saying the resistance is a lot lower than what your priors are. If this happens, just drop your priors down to say 0 and 50, something like that. The opposite can be true, where it does something like this to the max. If that's happening, increase it. But again, what can very commonly happen is if you increase resistance too much, like if you have it as an experimental value of say 200, but your optimizations are saying that the resistance is 1,000, something is just wrong with the other parameters, and the algorithm's changing resistance to make up for that. So be careful of that, and you can see that quite easily what will happen in the kernel density plots of RU, and a common one is K0, is you'll see something where it looks like this. It just kind of does something like that. And what's that mean is it's just the K0 is just, it's generally it would be the other way around of K0. So you can tell that it's just coupling. So it's dropping K0 and increasing RU. So if that's the case, you'll have to pin maybe another parameter, or just simplify, make a few assumptions based off what you chemically know in the system. Because at the end of the day, this is all maths, but we're doing maths to understand chemistry. If you're getting values that aren't right or don't make sense, it's because the maths isn't working well with chemistry. As a chemist, as someone who's fitting this data, you want the chemistry to work well with it, either by setting, say, alpha as 0.5, or setting diffusion to an experimental value. Two very common ones. You can also set K AA capacitance, E0, just change whatever. Another advisable thing is if you have that parameter set of all the values, just play around with it. Play around with what values work. If you're getting one where the K0 is equal to 0.1, that's pretty close to being fully reversible. So why don't you do the whole exact same thing with the parameter set, but you set K0 to being theta equals reversible. So that, and then you'll end up with a bunch of parameters, and say for K0 equals 0.1, diffusion equals something like 5.5 times 10 to negative 6 centimeters per second, centimeters squared per second. Say we get something like that when we allow K0 to be variable, and it calculates this plus or minus a standard deviation. If we set K0 to being fully reversible, let's say 1,000 centimeters per second, we end up getting a diffusion value which is something like 2.2 times 10 to negative 5 centimeters per second. That's just completely wrong. So if you get something like that happening for your diffusion, when you set the system as reversible, you know that it just isn't working right. So these values that it can output aren't, how can I say this? The algorithm is designed to give you right answers, but it can very easily give you wrong answers. And you have to play around and do stuff to make sure that for answers you're getting one, valuable for the chemistry, two, respectable in that they're not just overfitting to data and giving you a incorrect answer. Now, arguably, no matter what you do, your answer is going to be wrong, but some will be a lot less wrong than others. Like some will make 100% sense with the chemistry and will give you good insight into what's happening. Others will just give you absolutely no idea whatsoever. And it's important to understand that by playing around with specifically the Bayesian inference, you can identify what works and what doesn't work, or how your system responds. Due to speed, though, as these might take 4 hours to a day to run, I recommend doing as much as you possibly can by just playing around with the parameters in CMA-ES, using either TCDS or harmonic percentage. Then once you have a good idea of what your parameter values should be for either harmonic percentage or TCDS, move on to Bayesian Inference, CMA-ES. TCDS will struggle a lot at this step because you're going to have to calculate the noise as well, and the noise is quite arbitrary. It's generally pretty small. It'd be about 0.1% of the max current, so you can try and figure out what that is from there. But the harmonic percentage will do that very quickly. It does it extremely fast, moving from a non-Bayesian loss function to a Bayesian loss function. It does it extremely fast, so try that as well in CMA-ES, and it should work reasonably well. And then just play around with stuff. The Bayesian inference is where it's not going to run. Another thing to do is I strongly suggest using a bash function, and I'll just get something like that up now. Okay, so because we're going to be running a lot of these MECSim or CMA-ES, instead of just sitting at your computer waiting for like 10 minutes for CMA-ES to finish and then running another one, or for BIOMEC waiting there for 4 hours, you can just queue it all to run using a bash command like so. So what this will do, I don't think for weight's 100% required, but it is required for supercomputers. You just submit a bash command file with this here. And what it'll do is it'll run biomec.sming and then take an input. Here we've got the same input twice because I forgot to Control-C, Control-V correctly. But for a third one, here's a different one here. So you basically just queue up all of these and then run it sequentially. So it'll run this. Once that's finished, it'll run this. Once that's finished, it'll run this. The important thing is that it has a top part here and has the .sh file here. And to run the whole thing, you type in bash script ... .sh, and that will run all of these queued sequentially. So you can, if you've got a lot of these to run at once, you can run it for a week on a computer or on a supercomputer, come back in a week and see what you've got. That's strongly advised. Just for speed. Is there anything else we really need? TCDS, harmonic percentage. One of the things with the Bayesian inference is when it couples, especially on the harmonic percentage methods, when it couples in sets of 3. And one I know about is K0, diffusion, and RU. So all of these interact. K0 is inversely proportional to RU, D is inversely proportional to RU. And what ends up happening is you end up having 3 parameters interacting with each other so that you can never really optimize to a good fit. You'll always get really weird values of your parameters. Again, the best way to do this is probably just to set RU, but if you had a different parameter there, you would just set the easiest one, or the one that makes the most sense chemically to set, you would set that. And that works really well. The other ones are just convergence, optimization. For the MECSim C1, once you tell it to run once, if you don't optimize to a good fit, you can't add that on and then keep going. That's wrong, and you have to redo the whole thing. So it's advisable that if you do something first time to test how many you need, do a few quick ones at 250,000 iterations at 4 chains. That'll give you a good idea of what your parameter set is. And then you can basically see whether or not everything is working. And once our hat values are lower than 0.02, well, 1.25, you'll know that you can basically just say, okay, this is good. Hang on. 1.025. You can accept that these are once you identify that R hat is less than 1.025, you can basically just say, okay, well, we can run less and less simulations. And if you were to plot, say, R hat as a function of iterations, you might see that you only really need, say, 4,000 per chain. So that would be a total of 106,000, 16,000. So if you only use 16,000, all your MECSim calculations will speed up nearly by a factor of 2. So it's just about decreasing the number of simulations you run, decreasing the accuracy, and increasing the number of CPUs or number of chains. And all of these will increase your overall speed of your Bayesian inference, which will, everything will just fit a lot faster. If combined with a good bash file, you can end up getting stuff very quickly, or testing multiple things at once. So you're not wasting much time, or your computer can just run for extended periods of time without you worrying about having to go back and check it all. Yeah, so that's pretty much everything I can think off the top of my head. I can think of a couple of things to read if you need more information. A student's guide to Bayesian statistics is a good one. I'll link that in the description. The original paper that this, the one we did with David Gavavan's group is also very good to read, so I suggest reading that. The original BIOMEC's also quite good, so in case you have more to worry about, or more interest. Again, the big principle is this is a mathematical technique. But you want it to do chemistry. At the end of the day, we're trying to solve chemistry. So you should, in essence, just use it to solve said chemistry. So any values you get, you need to double check, are these values valid? And any values, because the computer doesn't understand the chemistry, that's our jobs as researchers to understand. So we need to add that prior information, in essence. The computer will treat it like a mathematical problem and just find the best fit. And that might not be chemically what is the best fit. To wrap this all up, computers solve maths. We want for chemistry. And what I mean by this is, end of the day, the computer's going to treat all of these like a maths problem. It's going to try and find the solution and what it actually represents. We don't technically want the solution. We want the most chemically correct solution. So the difference between what we want and what the computer wants is going to cause quite a bit of issue. And we need to, one, tell the computer the best way possible to get the chemistry. And secondly, we need tell the computer how we want the maths to work so that we can get the chemistry we want. And we also want that any values we get from the computer to be chemically valid. And that's something we have to consider whenever doing these kind of things. Another thing you want to do is to speed up the calculations where you can. Or speed calculations up where you can. Basically, just if you can get away with using slightly less accurate MECSim simulations, do that. Because if you drop every number you drop that down by, you're going to speed everything up by a factor of 2. If you don't need as much accuracy for your CMA-ES optimizations, increase the tollx function so it doesn't iterate for as long. If you are doing Bayesian inference, first add more chains, and where you can add more chains, decrease the overall number of simulations you're doing. So that every chain you add is going to increase it up by a factor, and every decrease of simulation is just going to speed everything else up. Another thing is just probe the system where you can to save time. Most of these systems you're going in completely blind or majoritively blind. So you need to basically probe the system where you can to get as much information as possible to just kind of understand how everything's working, understand what is working, what isn't working, and just do that. And fourthly, design the chemistry to work with the maths. So these, again, are all maths. You want to make sure that the chemistry not only gives you mathematically sound solutions, but the mathematically sound solutions then work well with the maths. So if you're going to do anything like K forward, K back, you're going to want to make sure that the sensitivity is in the chemistry to extract out the maths by just smart parameter changing in the experimental design. Also, just make sure that the chemical data is good. These methods can work well in optimizing when the chemical data isn't good, but it will bias the data, or the computer will try and compensate for it where it can. And that compensation can lead to really odd parameter values. So where possible, make sure that you can change experimental design to make more valid sense. Probably a very good example of this is absorption. Absorption for FTACV will lead to very weird looking harmonics where certain lobes will be much larger than others. And the computer will try and optimize for that the best way it can. And you don't really want it to do that, because beneath the absorption, there's a perfectly valid solution there. So you'd change that by decreasing the concentration of analyte or just changing the electrolyte concentration, all of which can really help by changing the chemistry. You can really help the maths. Overall, thanks for watching my tutorial. I hope you've all enjoyed it. Well, not enjoyed it, but got something out of it in the end of the day. And remember, rate, and subscribe. All the casual YouTube stuff. I don't know. I have no idea what I'm doing. I hope you learned something. Thanks.